That's a really great presentation. It really is an interesting topic. There's actually a video. I was interested in scramjets a while back. There's a video that you can see a plane fires the missile and the scramjet is attached to the missile. And then once that missile gets to speed, it drops the scramjet. And then you see the scramjet take off, a lot faster than the missile is traveling. So there's a video, you can watch it, maybe on YouTube. So great presentation, great topic. For the next presentation, I'll introduce the speaker, Mr. Andrew Wellmeyer. He will be giving a presentation on the future experiment that we'll be doing, the clay baron experiment.
Where's the red light? Is it happening?
Oh no, he just said it.
Okay.
Yeah.
You gotta press it really hard too.
This one?
Yeah.
How's it going? I'm Andrew Wellmeyer, and I'm giving these lead presentations for the platform experiment. And first of all, this is the Clapeyron equation. And pretty much what we're going to be doing is we're going to be taking this apparatus over here, and we're going to find the dP/dt curve, or the saturation pressure curve. This one right here. Y'all probably remember this from thermodynamics. And this is the relationship that we're talking about, the equation, and when you combine it with the ideal gas equation, and you get this right here, and this is what we're going to be using to do our calculations. So, our objective in the experiment is to record the data, like I was saying, and we're going to use this to find the enthalpy, the difference in the enthalpy between the gas and the liquid state. So, for all of you that don't remember, the enthalpy of gas, enthalpy G minus enthalpy F equals Fg. So the gas is a certain enthalpy, the vapor inside the test tube, and the liquid is a certain enthalpy. So the difference between the two is what we want to find. The amount of energy that you have to add pretty much to change states. And it's proportional to the slope of the curve that we were talking about. And for this is actually and it's decreasing for the train for water. And I think that this one just is increasing because of the units and how the graph is laid out. But if you look at this curve, which is what we're trying to find right now. So this is relative, you use it anywhere where you have some kind of phase change, mostly between the gas and liquid state. So if you're working with some kind of mixture of liquids, you're probably going to want to find out what their enthalpy formation is, because everybody remembers that when you have mixed liquids, then the properties change. And this is our apparatus right here. This is our data position. This is our test tube, the heater, and pressure transducer, site gauge, and thermocouple. And this is our vacuum apparatus right here. Basically, it's a Venturi pump. And so, when we turn on the pump, it's going to pump water through here, and it's going to pull a suction on here. And what we're going to try and do, ideally, what we want to do is to pull this down to where there's no air in there. So we can have just vapor and just liquid. But we're not going to be able to do that because these pumps are not that good. And we'll be heating this up so it comes up to the wall, obviously. Alright, so our steps, first thing we're going to do is we're going to pull it back in from the beaker. We're going to pull out all the air, like I said, and then we're going to start heating it up to bring it up to a boiling temperature. And then as soon as it starts boiling, we're going to start logging data. And then is atmospheric. Then we're going to turn off, we're going to stop taking data. So some thinking points, boiling temperature is going to be lower than 100 degrees C because we're in a vacuum. And true vacuum will not be reached because our pump is not good. If you used, for example, a vane pump, a vacuum pump, like they use for air conditioning work, then you can pull a real vacuum on it and you can have pure vapor and pure water, and get better experimental results obviously. And with the boiling beads, you get a little different behavior because the boiling beads cause a more vigorous boil. Kind of increases the surface area of the heat source, so it boils a little bit harder. And why do we start by cold vacuum? 3 times, right? And so why do we stop at atmospheric pressure? Mostly because our setup is arranged for lower temperature. If you increase it past atmospheric pressure, then the stopper is just going to pop off. You're not going to be able to get that out of it. So for our assumptions, whenever we get to maximum vacuum, we're going to assume that there's no air in there. Even though we know there is, we're just going to say that there is for the purpose of the experiment, so we can rely on our data, or we can pretend to rely on our data. And we're going to assume that the thermocouple and transducer are calibrated with our system, and that they're in good working condition. And we're also going to assume that there's a uniform temperature in the water and the vapor. If we're going to calculate a relatively accurate enthalpy, change in enthalpy, then we have to assume that there's a uniform temperature all the way throughout. Otherwise, you're going to have differences in enthalpies in the vapor and in the liquid. So this is the data that I got from online. And I tried to be an overachiever and take 2 sets of data. And as you can see, they are not even close to being alike. So that's, I guess, what I get. Trying to be an overachiever. This one came from San Diego State. It was just on the website on a data table. And this one came from engineeringtoolbox.com. And I have 2 graphs because the temperature range is much higher for this one. But they're still not even close when they're opposed to each other. So to calculate the uniformation, or the difference in the enthalpies, well, we're going to use the equation that I showed you already. Just the slope of the saturation pressure curve times the other part that's mixed with the ideal gas curve, or the ideal gas formula. And this is all the tabulated value of it, which I'll explain that. So this is these are the points that I took. I took 6 points for each one, just because my data was so dissimilar that I wanted to do a little more thorough analysis. So it turns out that the San Diego State curve was the one that was way off, and the engineering toolbox curve was much more similar. And these are my calculated and tabulated values, and there must have been some. Well, you can say that there's something wrong, but I rechecked my calculations, so who knows what happened there. But for this curve, they came out nice, and for the tabulated values, they looked much better, but they still weren't that good. And one thing to notice is the difference in the ranges here. These are much, much higher. And the only thing that I can think of is that the calculation of the derivative that I did was a little bit off. So that would be something to look into, but I don't think I have time to go into that. So for our expectations for the experiment, expect error, pretty much. That's all we can really expect. There's a lot of different ways the air, like I said, we're gonna have air inside the beaker. And we're not going to be able to get down to full vacuum, so we're not going to start at the pressure that we want to start at. And all the equipment in here is old; it's been used 1,000 times. So, and there's no way to really accurately or scientifically take in the weight of all the effects of these errors. So, really isn't an analysis to do on. I've actually come to the conclusion that they have made all these experiments in here intentionally inaccurate, so we have a lot of explaining to do when we get the presentation. So, and I think I have enough time to go into the derivative calculation. Now, what I did was I just did the easy way, and I took, which is probably the worst thing I could have done for the data that I had because of the spacing. And what I did was I just, with these that, I just took the next available data point over the change in the temperature, and it just gives you a derivative curve relative to the next available data point. But when you have spaced data points, and so you have, if I had a table in front of me, I can show you. But just because of the range of the data points, and there's more points at some parts in the curve. Like say you want to cover a high value, but you want to cover a lot of points at the lower end. Kind of hard to explain without a curve in front of me, but and so that's one way that I probably the calculations are off. And then also one of the tables I had to convert from metric to standard, so that might mess things up a little bit too. So anybody, any questions?
Did the other sources like San Diego State, did they describe like if they used a similar apparatus for their data?
They were just data tables online. The only reason I know they're from there is because the name of the website.
Right.
Yeah, no idea.
The derivative was pressure and temperature. What other method is used to get more accurate, like co-graded?
Well,
Since you know that, taking points, obviously we get it.
the method that what's the word? The directions give you, or the problem statement for the man, I'm blanking on my terms right now. The method that the procedure gives you for the data calculations, they want you to do a curve fit and then take the derivative of the curve fit. But I really don't like doing curve fits in Excel. I've done it before and I've wasted hours doing it. So I went ahead and did it the other way and decided to explain it instead of having just a terrible curve fit.
Why did it on curve fit? What would you do?
If I had a curve fit, then you would get your equation from the curve fit, you take the derivative, and you can say for whatever point, then you have your derivative.
Why would the water boil less than 100 degrees Celsius?
I'm sorry?
Why would the water, what we're expecting it to boil less than 100 degrees Celsius?
Because the pressure is lower. So it lowers the boiling temperature. The pressure inside of the beaker is lower than atmospheric, pulling a vacuum on it. Anybody else? All right, thank you.